All right, let's dig in. Let's keep going. We have invert binary tree as next. Let's take a look at what that says. I figured out how to make the colors dark. There's a setting in Chrome you can do. Doesn't fix everything, obviously, but it fixes most of it. Given the root of a binary tree, invert the tree and return its root. Okay. So it's just basically flipping everything around. We can do that. We're going to need to implement this thing like we did with the list. We're going to have to implement TreeNode. So let's figure out how to do that. So first things first, we're going to source lib. Oh, that's right. It's in utils. So if I just jump to utils real quick, I said jump to utils. There we go. We have list. So now pubmod tree, pub use tree, star, and tree doesn't exist. So let's create it. And we can just steal this. This is the implementation here. Copy paste. And then we just need to create delete all those. I'm going to change this to self like we did last time, just because I'm a stickler for that. I'm not sure the inline helps at all, but I'll leave it. And then we need to figure out how to create a tree from a vector. So what's the format here? The input is 4271369. So it's just 4271369 like that. And the output is 4729631. Okay. And here's 213. We should do 231. And then empty is empty. All right. So the way this works then is it's based off of the offset in the array. Like this is the root, this 4. Then 27 is the next level. And then 1369 is the next level. The fact that the array ends right there means we're done. So in order to create a tree from this kind of a vec, I think we need to calculate out the values properly. So we'll create a from vec like we have for the list. And we'll just take in some values and return an option rc ref cell TreeNode. Let's just return none for now, just to see if this will compile. We have test mod. We should be able to create an empty tree. Which should return none. Right, empty tree is just none, I believe, if we follow this logic correctly. We should also be able to do this, and then, maybe what we can do is create a walker, which walks it in sorted order, because this would be sorted. This would be 1, 2, 3. If we do it in fix order, right? 1, 2, 3, 4, 6, 7, 9. Maybe that's what we need to do. But let's just start off seeing if we can build one. So TreeNode from vec and an empty vec. And that is none. And that means this, like that. And that failed. Oh, RC and ref cell are not here. Use standard RC, use standard cell, ref, cell. Anything else we're missing? We do have 2 warnings. That's because val's not used. Okay, and the test. I'm guessing the test worked. It said finished running tests. But we don't have any test output, maybe because Bacon is just keeping this. All right, so that means if I put an underscore here, will Bacon show me the test output? It will. Good. All right, so If vals is empty, we don't need to do any work, return none. And if it's not empty, then we need to create the tree starting at a given node. So each index is a tree. Let's see this. So this is right. So since it's a binary tree, we're going to multiply index by 2 and then either add 1 or add 2 to it to get the left and the right. That's the way it's going to work, right? Yeah, so index 1, and then we can add 1 or add 2, and then 7, we're going to add, multiply by 2, right? Because it's 4, and then add 1 or add 2 for the left and the right. So I think it's just index times 2 plus 1, and index times 2 plus 2. That should... I'm basing it off my memory of how to do this conversion, so I might be a little off. What we could do is just create the node, the head node, or root. We'll use their new function and make the root node, and then let's create a fill function. That way we can do it recursively. So we could just say self fill. Oh, that means this needs to be mutable. The vals, and we'll start the root node at 0, and then we just fills will just go left and right, and then we just return the node, the tree self. Okay, so fun. This doesn't need to be public. So itself, we have our vals, I32, and then the index that we're going to start with, which will just be an index into the vals array. This doesn't return anything, it just builds on root. So we're going to have a, we're going to check index times 2 plus 1. Index times 2 plus 1 is less than vals.len. Right? If we still have an entry in the array, then we want to make a left node for this. So self left equals, and it has to be this format here. So it's going to be sum RC new, ref cell new, and then a tree node, which would be self new, and then vals of 2 times, or index, let's use the same format, times 2 plus 1. No, that's a lot, isn't it? And then we're going to recurse at that point. So we'll say self left dot, and it's an option, so we need to unwrap it. And we know it's going to be sum because we just assigned it, so we don't have to worry about that. And then borrow mute for the ref cell, and we're going to fill that in with vals starting at index times 2 plus 1. So you know what we could do is just we can calculate root node. Let root node is equal to index times 2, or let's say left node, plus 1, and then we'll just add 1 for the right node. So if left node is less than vals than that, and starting at the left node, and then we can check to see the next one. So if right node is left node plus 1, so left node, right node, left node, right. Oh, that's pretty simple, but it makes the code, I think, more clear of what we're doing. Vals len self right is equal to sum rc new ref cell new self new vals right node, and then self right unwrap borrow mute fill vals right node, and that's it. That should recurse down left and right side and build a tree. And so we can actually print that out after we're done here. We'll do the test self fill and say self println tree is equal to self debug out. Okay, now we have to see if we have debug on these things. We do. Okay. And that fails because I'm missing a brace somewhere. Left node is less than vals len. This is where it's complaining. Oh. There we go. There was too many of those. Self value is keyword only with the self. Oh, root fill. From vec requires a self. No, it doesn't. I don't want a self there. I want a root here. There. Why does it still want us? Oh, because root. Man. Some RC new ref cell new root. Oh, right. And then these need to be as refed. Okay. So we're still able to build an empty tree. Let's see if we can build a fuller tree. TreeNode from vec. I'm just going to say is none, and then that way it'll print out what it is. Let's just copy this. Like that, and then just say is none. And then it should fail, and it should print out the tree, and it does. So we have a 4 for the root. That's right. The left has 2. And the left of that has a 1. The left and right of those are both none. The right of the 2 has a value of 3. Correct. And it has a 0, a none for left and right. Then we pop up a level, and we have a right on 4, which is going to be 7. Correct. Then its left is a 6. Its right is a 9. And then panic because we didn't get a none. Okay. So I think we've successfully built the tree. It'd be nice to be able to print that out. I don't know how to test that we got it right in any other way. So let's write a walker for it, which generates a vector. Let's do that. Pub_fun into array of self. And that'll just return a vec of i32. That way we can actually test it. And then in order to do this, we basically just want to return a walk, self walk. How do we want to do this? How do we want to do the walker? Something. I guess what we could do is just say this, and just say let mut result equals vec new. And then just have fn walk, which takes self and a result. That way we can just walk and push. Right? If let sum left is equal to self left, then we want to walk the left, borrow, walk result, and that'll push the left side on. Then we want to push the current node, result.push self val, and then we want to walk the right side. If let sum right equals self right, right.borrow walk result. Right, that should push it in order. And then what we can do here, do I still the print? Yeah, let's get rid of the print. And then what we can do is just say here, let tree is equal to this. And then we can say let result is equal to tree dot into array. And then we want to say assert eq result is equal to 1, 2, 3, 4, 6, 7, 9. Let's see if that works. Nope, because tree into array doesn't exist. Oh, it's not found on this. Okay, so we have to say tree unwrap borrow into array. Yeah. Okay, so this just verifies that we're able to build the tree using this kind of a thing. And that'll be useful for testing, right? Not necessarily useful for solving. But the tests are the important thing. So I think this is the basic tree design, right? We can build this tree, we can build this tree, and we can build a null tree. So let's commit these changes. Git add source, git commit a basic tree structure.